program called ICTP diploma program, focusing on condensed matter physics. That was in 97, 98. So we enrolled and graduated at the same time. And after that, Narayan immediately got accepted in the university somewhere in Germany, I guess somewhere in Halle, right? Yeah, I don't remember that. Well,
Martin Luther University.
Martin Luther King, yeah. King. Whereas I only, I got accepted by a university in the United States only later on.
Yeah.
So, and I think since then, since obtaining his doctoral degree, Professor Adhikari did some postdoctoral work, right?
Yes.
And finally, he came back to his home country.
Yes.
To have the scientific career as a professor. I mean, he started from, perhaps you started from being assistant professor, right? And then
yes.
And as of now, Professor Narayan Adhikari has been a full professor, right?
Yes,
in his department. And today we are happy to have him with us to share his research, his knowledge about molecular dynamic simulation study, and especially about the repair mechanism of certain DNA. So I don't know more than just the title that I saw, from the from the poster that that we have. So let's just pay attention to his talk, and feel free to ask questions.
Yeah.
And I myself also want to probably ask and as many questions as I can have if nobody. Well, hopefully, I really hope that students will raise questions. Okay, I think without further ado, I give the time to you, Professor Adhikari, please.
Okay. Thank you, Professor Majidi, for giving me this opportunity to discuss what we are doing here at your university. Am I audible? And
yes.
Are my slides visible?
Yes, it is.
So good afternoon, everybody. Today I would like to discuss about this repair mechanism of AGT for methyl-induced DNA damage. And before moving to that, I would like to discuss how we started molecular dynamic simulations in Nepal, methylation of DNA and its transfer to cysteine, the main topics of today's presentation. And if time permits, then I will discuss about protein-protein interactions, focusing on understanding physics behind COVID-19. So as Professor Majidi mentioned, I first did my postgraduate diploma in condensed matter physics from ICTP. Then I went to Martin Luther University, Halle-Wittenberg, did my PhD. From there, I went to Rice University, RPI, and Max Planck Institute, where I got an opportunity to learn about DFT, molecular dynamics, etc. So after then, I joined Trivandrum University, which is this building actually. And the main goal of university was, and still it is, to teach students. Research is just the interest of faculties. I had to teach many courses like structural mechanics, solid state, advanced solid state physics, condensed matter physics, UFT, computational physics, like this. So there was actually, we did not have any research laboratory at that time, not many computational facilities also. However, we have, and we had also large number of students, 120 intake in MSc in physics at Central Department of Physics. If you count total number of MSc students at our university, sometimes it was 720 intake to start any research work, which gives us a bit satisfaction. So there were two problems to start the research work. One is to get research journals. Being in Nepal, it's not so easy to get articles. And that is actually fulfilled by ICTP EJDS service, Electronic Journal Delivery Service. I'm sure all of you are using this. In Indonesia also, you can use it for freely. Once you register, you can just get all the articles, whatever you are interested in your email immediately. And to start the simulation work, we needed some computers also. That's what, at that time, when I started EMD, I really did not have any one computer also. Then I asked one of my students in United States to provide. And one of my students actually finished his MSc dissertation, and we published this article also, his manuscript in some journal also, like oxygen in water, simple simulation of simple systems like oxygen in water. Then ICTP provided some support for desktop. Then again, ICTP provided more supports for few more computers, PCs, generator, and started supporting our students. Then was the old academic sciences supported for computing facilities. And now we have 5 server machines, our own solar system, uninterrupted power supply of 2.5 kilowatts, so that we can run our jobs anytime. Because there is this load shedding in our country, so we needed this uninterrupted power supply also. Of course, our systems, if you think about our systems at the beginning, they have to be it's very small due to limitations of computational facilities. However, we tried to focus our attention from very simple to a bit more complex, like systems which are environmentally significant, from ozone, oxygen, water, biologically significant molecules like water, amino acids, physics significance like neon, argon, krypton, etc. And they provide us one of the ways to test the ideal gas behavior also. And in our daily life, we use polymers, biopolymers like DNA, RNA, protein, etc. And our current main interests are DNA protein interactions, protein interactions of SARS-CoV-2 virus and human S2, and atomistic coarse graining polymers like this. So because of this, our department also started producing few articles, like in Journal of Molecular Liquids, Physical Review B. Recently, we published solid state communication. Even though the area was a bit diverse, we could give some idea to our students in fundamental physics how to do research like this. So I supervised at least 75 MSc students from our university. All of them are currently in USA. Some are faculties in many universities like Florida University, Rochester, and so on. And some are still doing doing their PhD. I mean, the first students whom I supervised, they are almost all are faculties in USA, and some are in their middle career, like doing postdoc, and some are carrying on PhD. of course, it's really difficult to carry research in places like TU. And if our number of students will decrease, then we'll get more opportunity to focus on research. And recently I got this number. Actually, if you see, non-US physics PhD degree recipients from classes of 2017 and 18 combined, from Asia, there were 70% students. Out of them, 30% were Chinese, 15% Indian, and Nepalese 7%. Means our number comes in third. If you compare foreign students getting PhD degree from US universities. So this is what we take as our strength also, because we try to motivate our students by our research work or some other teaching ways to pursue their career in physics, even though all of them are not in our country. And our work, once it was featured in Nature magazine, also developing old far-flung physics. So this is what I wanted to talk about, my background, how we started our work in our department, university like this. Now I would like to focus on DNA protein complex. So what we have this DNA and this is protein. They need to combine, they need to talk each other. There is some interaction between DNA and protein. What we wanted to understand is that when they interact, is it really useful for us from some point of view? For example, what happens? This DNA gets methylated. DNA has one part so-called guanine. This is guanine. This is structure, I think everybody is familiar with such things. And there will be this methylation. CH3 comes and attached to this. So this is not good for our health. And sometimes it transfers to protein. When this DNA and protein interact, then this methylation of this DNA transferred to this protein. This is one of the amino acid of protein. This is cysteine amino acid. And what happens? This methylation transfers from methylated guanine to methylated cysteine. So in this way, this methylated guanine repairs itself. And people were saying that such process can happen in our body many times. And this is normal process, natural process like this. So as a physics student, what we wanted to understand whether such things are possible energetically or not. We did some classical molecular dynamic simulations to understand this interaction between DNA and protein, and to check whether such transfer of methylation from guanine to cysteine is automatic or not, is spontaneous or not. For this, first we prepared two molecular systems. One this without this methyl adduct and another with methyl adduct, and we propagated 100 nanosecond simulation run for each, and we tried to understand the patterns of hydrogen bonds. Generally in our biological systems, these hydrogen bonds, van der Waals bonds, and this they play very crucial role. Apart from this ionic bonds also, of course, Coulomb interaction is there, and they help for such bonding also. Then when we studied this hydrogen bonds, then we found that these guanine 7s O6, N1 and N2, and cysteines, oxygen, N3 and N4, they interact. I mean, there is 3 hydrogen bonds in non-methylated pair. And 2 hydrogen bonds if it is methylated. So non-methylated is more stable than it looks this methylated pairs. So with this figure shows, this graph shows actually number of hydrogen bonds versus time. Because of this limitation of computational facilities, we ran our job for 100 nanoseconds and 300 nanoseconds. There are 2 different types of runs. And when there is no methylation, there are 3 hydrogen bonds. When there is methylation, there are only 2 hydrogen bonds. And then we studied this, whether our system becomes stable or not. So for this, we studied this stability by studying this burning pattern of this NH2 and N4, N3 and O2 like this. And we observed that there is this hydrogen bond, clear hydrogen bond between NH2 and N3. That's what we can see from pure distribution function in this graph also. This graph shows that this blue one actually is radial distribution function of NH2 and N3. The distance, mean distance between these 2 entities is most of the time 3 angstrom. So this means they form a stable hydrogen bond. And if you see NH2 and N4, this N4 nitrogen, then the distance increases, hydrogen bond becomes weaker, and that's become for very short time also. And if you see this hydrogen bond between NH2 and O2, then this distance again becomes farther. I mean, the distance becomes farther, and hydrogen bond becomes weaker. That's what we checked it from this distance versus time graph also. This molecular dynamics provides us opportunity to understand, to see this trajectory of our atomic molecular system as a function of time. From that one, we analyze the we predict different properties of the materials. So cysteine 20, the cytosine 20 and arginine 128. There is the distance is consistent. This blue one. Then what we did, we prepared 3 different systems. One system, this protein, DNA protein complex, which is not covalent, non-covalent linkage between this DNA and protein. Another, we prepared covalent complex. There is covalent bond between this cysteine and guanine. And we prepared these 2 systems. From these 2, we actually made 3 systems. This non-covalent complex, actually, we made it for pre and post methyl transfer. Pre-methyl transfer means, okay, pre-methyl transfer means this DNA and this is protein. This DNA guanine is methylated somewhere here, and this is this one has been highlighted in this figure here in right side. This is methylation of guanine, and this other is cysteine from this protein molecule. And another, this complex third, is this methylation of this guanine has transferred to cysteine. DNA and protein are still interacting, but methylation of guanine has transferred to cysteine. Intermediate transient state is that this cysteine and guanine through these sulfur atoms forms a covalent bond. But this is very, happens for very short time, and this is transient state. So at the first, what we did, we prepared 3 such systems, and we carry on molecular dynamic simulations. After designing force field for this case, some force field we took from literature, some we asked to our collaborator, and some we designed ourselves, because force fields are very important in molecular dynamics. So we prepared such 3 complexes system. First one, this complex one, DNA methylated, complex 3, cysteine methylated, and complex 2 transient state. This is this 2 cysteine and guanine, I mean protein, one of the amino acids of protein and one of the nucleotide of the DNA, they are combining, they are interacting by covalent bond. So then what we had to study, we designed our system, we had a force field like this, and then what we had to do, we must study their stability, whether they are real or not, the systems are stable or not. For this, we ran our job for about 200 nanoseconds and studied this root mean square deviation of the distances. And since they look like stable for about say 200 nanoseconds, we became sure that our systems are stable, and we carried on further study. For that one, we studied the interaction of nucleotide and residue pairs. And there are actually, we find out 2 different sites where this nucleotide of DNA and one of the residues, I mean, one of the amino acids of proteins interacts with DNA. And from site 1, there are this nitrogen and hydrogen oxygen interacting. In this case also, they are interacting. And we basically detected from our study these 2 major binding regions, these 2. And guanine 7, this guanine 7, thionine 9, and thionine 23 are this thionine 9 and 23 are main interacting nucleotides actually. That's what we figured out from our calculations. Then in all the 3 cases, we analyzed hydrogen bonding, because hydrogen bonding plays quite crucial role in biological systems. So this figure shows hydrogen bonding versus time. And this blue one is for complex 1, means DNA is methylated. Green one is protein is methylated. And this complex 2 red one is for transient state. So hydrogen bonds are consistent in complex 1 and 3. But in 2, if you see, after under 30 or 40 nanoseconds like this, they are decreasing. This is because of unstable intermediate state. And it has close agreement with some quantum mechanical results reported previously in some literature. Then we tried to find out the distance of major interacting pairs. And there are these 3 main interacting pairs. One is 6OG7 and tyrosine, 6OG7 and cytosine, cysteine, 145, oxygen actually. And the distance looks like very stable, say 3.5 or 3 like this. In this case, 6O7 and tyrosine 114OH, 6O7 N2 nitrogen 2 and cysteine 145 oxygen. Both have distance till 200 nanoseconds of about 3 angstrom only. Similarly, this for the 6O7 N3 and 6O7 N2, this tyrosine 114 and 145, they have this distance a bit higher also, and so on. The distance are anyway more or less consistent. This backbone of 6O7 guanine 7 and side chain of tyrosine are more consistent. Distance between backbone of 6O7 guanine 7 and backbone of cysteine 145 is more fluctuating here. And this result agrees with transition path sampling method, which was reported before. Then we studied this root mean square fluctuations. This figure shows root mean square fluctuation versus these different residues for 3 different complexes 1, 2, and 3, what we prepared. And these root mean square fluctuations are not significant. They basically gives this RMSD gives actually global properties, and this RMSF gives local properties, local fluctuations, how much this residue only fluctuate like this. And maximum flexibility observed in residues region between 35 and 52. It happens here in F1. And residues at F2 are stable in complex 2. In F2, if you see, the residues are stable. Then another property to check is contact surface area of DNA and AGT. You see, what we are doing, what we are studying is we are studying this DNA and protein interactions, and how this surface area between them, this interacting contact surface area between them changes by time. That is also one of the interesting property to study. So here, this table shows complex 1, 2, and 3, and contact surface area in angstrom square. This net contact surface area becomes in complex 1 894 angstrom square, in 2 909 angstrom square, and in 3 878 angstrom square. In complex 2, higher contact surface area is understandable because we have there this, even for very short time, transient state was, this covalent bond was there. So this is consistent in complex 1, decreasing in 2 due to unstable binding. This figure actually presents the contact area, these areas, as a function of time. This table shows average of everything, but this figure shows contact surface area as a function of time. Then to understand this binding mechanism, whether this transfer of methylation, this CR3, from DNA to protein is possible or not. To see this, we carried on SMD simulation, so-called stirred molecular dynamics. In stirred molecular dynamics, we keep one molecule, for example, this DNA is here. We just pull this AGT in this positive X direction like this. That's what we did. So 30 nanosecond SMD in complex 1 and complex 3rd. This is called system 2 here. And then we studied the contact area. This contact area decreases in system 2 suddenly after, say, 10 or 15 nanoseconds like this. However, in case of system 1, it remains almost constant. And after some time, decreases, but still this is play to light. This means if contact area is less, you can detach them easily. This means the decoupling in system 2 is easier than system 1. This means, okay, if you have two systems, methylated DNA and methylated protein, methylated protein system is easy to decouple than methylated DNA. So to understand more on this thing, we try to find out main binding sites of DNA and AGT, and site 1 is stable in system 1 but decoupled in system 2. If you see here, site 1 is somehow coupled, but if you see in this figure 2, in system 2, it is decoupled. So this is what is consistent with our previous result. And then what we did intramolecular decoupling. In intramolecular decoupling, we have this DNA and protein, and there are 3 different sites of interaction. Site 1 and site 2 are DNA protein interaction, whereas this site 3 is protein. And what happens actually, breaking of hydrogen bonds and aromatic contact in region 3. That's what it happens. And intramolecular breaking in region 3, main cause of stretching loop in AGT. Then what we wanted to understand this, how much decoupling force we need to detach this protein. So for this, what we did, 5 independent assembly run executed for both systems and system 2, and we need to pull it. This pulling velocity is 1 angstrom per nanoseconds, and we analyze this graph force versus displacement. There is highest force in different runs. This is for system 1 and this is for system 2. And then this figure third shows average force for as a function of displacement. For system 1, blue one, and system 2, red one. For system 2, you require less force than system 1. So maximum decoupling force is required for system 1, and that is around 900 piconewton, and system 2 approximately 750 piconewton. AGT does not leave DNA, but its activity degrades, agrees with previous result of AFM. And then what we did, we tried to estimate free energy. Free energy estimation can be done in such systems by various methods. There is this thermodynamic integration method and bar method. And then this much more robust method is umbrella sampling, so-called umbrella sampling. And systems like this, in which we are studying such big complexes, we don't have any other choice except umbrella sampling. So what we did, we carried out umbrella sampling simulation. For this, we translated DNA in negative S direction, keeping this protein in its place itself. Here, this figure A, B, C, D, E shows completely detachment of protein and DNA. And when you detach one system from other one, say protein from DNA, then sometimes what happens, the systems becomes unstable. We must be very careful to check that one. So to check that stability of our systems, because we pulled them at the beginning. Okay, when we started simulation at the beginning, we checked their stability. But what we did here, we slowly pull this DNA in negative x direction. So in negative x direction, we pulled them, and in 1 angstrom differences for 19 different times, means we pulled center of mass between them 19 angstrom. So there are 19 different samples. So we had to check stability of all these 19 systems, and complex 1 and 2 shows this figure A and B shows stability of complex 1 and 3rd, or RMST versus time for complex 1 and 3rd. And this figure C and D shows maximum displacement, maximum value of RMST and minimum value of RMST for these two types of systems. So this shows that this RMST is getting this behavior of plateau, means our structures are stable. So average value increases as center of mass distance increases. Then finally, what we did, we estimated the free energy difference of free methyl transfer. I mean, in this case, methylation was there in DNA, and this other case, methylation happened in protein, means cysteine, one of the amino acids of protein. So what we did, we calculated free energy difference between these two systems for taking 19 different windows, and all the windows were stable. And we estimated the energy, free energy in each angstrom. Then the pitfall, this minima differ just by 1.3 kilocalorie per mole. 1.3 kilocalorie per mole is difference between free energies when you have a system of methylated guanine and another system of methylated cysteine. This energy is very less, and this is less than or comparable to thermal energy in our body. Even though E raised to the power minus delta E by this delta E by kBT is a fraction, since there are many DNA protein interactions, our calculation shows that this transfer of methylation from this guanine to cysteine can happen energetically in our body spontaneously, because the difference in energy is 1.3 kilocalorie per mole only. So after then what we did, we analyzed the non-border interactions during translation. So this figure shows energy versus center of mass distances, energy versus center of mass distances. This is van der Waals interaction, and these are electrostatic interactions. Of course, van der Waals interactions are weaker, much weaker than electrostatics. These are electrostatics. Even though they look weaker, they are also important. That's what we know from our experience. So electrostatics interaction has dominating effect as expected, and they follow the trend of free energy curve. Majidi, how much time do I have? Can I proceed for 10 minutes more, or?
Yeah, sure. You can finish your talk, because we have time at maximum till 3. So you may at least try to leave 20 minutes remaining for
10
discussions.
to 15 minutes is enough for me. Okay,
Yeah,
thank you so much. Then another project, somehow related, but somehow unrelated also. The similar type, the same work, our expertise in DNA protein interaction, actually we extended to understand protein-protein interactions. What happened almost 3 years back, we know that there was pandemic, all of us were in home. I mean, you could not go to physics department to carry on research laboratory. You had to stay at home, but staying at home, using those computers, we try to understand how this SARS-CoV-2 virus binds with human H2 receptor. We know that this spike protein of SARS-CoV-2 and SARS-CoV both actually, they bind with human H2 receptor, and then this disease was there. So since this disease came, we try to work in this area, and I would like to discuss some of the results of that project with you. SARS-CoV-2 virus use actually human H2 receptor to enter target cells. Entry process is mediated by the spikes glycoprotein in SARS-CoV-2. Investigating major amino acid residues and interactions at the binding interface between the virus H, RBD, and host receptor. Free energy difference estimation by using umbrella sampling. This is what we want to do. So for this, what we did, we considered this human H2 protein and SARS-CoV-2, human H2 protein and SARS-CoV only, because SARS-CoV was also there, SARS-CoV-2 was also there. SARS-CoV just went and came and went away. It did not bother us much, but SARS-CoV really created a big problem. So that's what we wanted to understand by using our ideas of physics, how much binding strength, how the binding strengths differ for SARS-CoV and human H2 and SARS-CoV-2 and human H2. So for this, we prepared two different systems, protein of SARS-CoV and human H2, protein of SARS-CoV-2 and human H2. Then again, we did a study of RMSD versus time. And from this graph shows this red one is RMSD of SARS-CoV only, and blue one is for SARS-CoV-2. Means SARS-CoV-2 is much more stable also. I mean, this SARS-CoV-2 and human H2, this interacted. These two proteins are interacting actually in both the cases. RMSD is significantly less in SARS-CoV-2 case, means the system is much more stable. And what we did, we find out three different regions. Okay, this is CTD and this is human H2. This is CTD, means spike CTD. This SARS-CoV-2 protein, and this is human H2 protein. And we first did a molecular simulation work and first identified that three main regions of interaction. This spike protein interacts with human H2 at three different regions. These three different regions we actually identified first. That's what actually happened for SARS-CoV also. The regions of interactions are almost the same. However, there are some other differences between interaction of SARS-CoV and SARS-CoV-2 with our body, with our human H2 protein. So for this, what we did, we tried to analyze the number of hydrogen bonds, how these hydrogen bonds are stable by time in all the two cases, SARS-CoV and SARS-CoV-2, and then we wanted to quantify them. So, as already mentioned, in the case of SARS-CoV-RBD and human S2 complex, this is SARS-CoV-RBD, human S2 complex. There are three main regions of binding. This is what exactly happened in case of SARS-CoV-2 and human S2 complex also. And this figure shows the number of hydrogen bonds, occupancy in all those three different regions. This is for region 1, 2, and 3. And what we did, we compared the number of hydrogen bonds into complexes. This figure shows number of hydrogen bonds versus time. This red one is number of hydrogen bonds in SARS-CoV virus and human S2. Blue one is number of hydrogen bonds in SARS-CoV-2 and human S2. From this figure, we see that number of hydrogen bonds in case of SARS-CoV-2 and human S2 are much more consistent than SARS-CoV and human S2. That is one of the reasons, one of the ways, one of the mechanisms why this SARS-CoV-2 binding is stronger than SARS-CoV only. This figure shows the salt bridge interactions versus simulation time. Salt bridge interaction, source of salt bridge interaction is also electrostatic interaction. Here again we see that salt bridge, this SARS-CoV-2 and human S2, this red one is stronger than this SARS-CoV only. And then what we did, we compared the non-bonded interaction energy for two systems, energy versus simulation time. And this is this blue one is CoV, and green one is also for CoV2. They look almost the similar, almost same macroscopically, but if we zoom them out and analyze, SARS-CoV-2 is stronger than SARS-CoV only. And CoV electrostatics, SARS-CoV electrostatics, this red one, and SARS-CoV-2 electrostatics is this gray one, brown one, and this is higher than SARS-CoV-1. This explains that why SARS-CoV-2 is more severe in terms of binding energy of SARS-CoV and human body, and SARS-CoV-2 and human body. Finally, what we did in this case also, we carried out umbrella sampling and compared the binding energy, free energy binding energy difference. And in case of SARS-CoV-2, the binding energy is 1.91 kilocalorie per mole than SARS-CoV. This explains why, I mean, energetically, we can understand somehow that the binding energy of SARS-CoV-2 is stronger than SARS-CoV only. That's why this was creating problem for us. So finally, the conclusions: the demethylation of DNA is possible by AGT protein. All important interactions were relatively stronger in case of SARS-CoV-2 than those in SARS-CoV. Binding free energy of SARS-CoV-2 is greater than that of SARS-CoV by 1.9 kilocalorie per mole. SARS-CoV-2 binds to S2 with greater affinity than that of SARS-CoV-RBD. So my acknowledgement goes to my professors with whom I learned MD simulation, my students who carried out all this work, and the support was from ICTP TWAS for the equipments, for the computing facilities. Thank you so much. If you have any questions, comments, I will be happy to answer.
Okay, thank you very much, Professor Narayan Adhikari, for nice and very informative talk you have given us today. The topic is actually quite interesting, although probably I have to admit that I was not able to follow all the details because a lot of foreign things to me. I mean, new probably chemistry terms, right?
Yeah,
So even from the aspects of terminology that already gives me a problem, you know, to follow from one step to another. But I myself at least tried to understand the big picture of what you're talking about, and especially when it came to the end, when you related your research to, you know, how we deal with COVID-19 problem, right? So that even made the talk more interesting. So before myself come up with question, I'd like to invite everyone who may have a question. Please feel free to directly ask to Professor Adhikari. Anybody? Or if not, you can type in your question on the chat. Well, this is this is the online form for attendance.
Okay.
Yeah. Well, feel free if you like to fill out also, but it is not really obligated for you.
Okay. I can fill it up.
Yeah, we demand the participants to, but that's good. So if you fill out the form. Okay. In the meantime, please, audience, probably let me see who is here. Okay, students from maybe medical physics division, master's program in medical physics. If you may have some questions, the questions are not necessarily about the, you know, the technical details about the simulation. You can as well ask questions from the just general aspect,
Yes.
whatever. So Prof. Jarwani, are you still here?
Yeah, I'm still here.
Yeah, Bujar.
Yeah,
any
but
question?
I'm sorry, I cannot understand because so many terms I do not understand too. Because you see, the focus of medical physics and for this Ratuyo biology actually, we focus to study, yeah, the DNA, how the interaction the DNA with the ionizing radiation, yeah. So I think we if just like Professor talk about the DNA with proteins, yeah, special proteins, yeah. So maybe I think before, yeah, that maybe in the future, so you can DNA cancer DNA can be killed by special proteins and I don't know, and this is the future maybe. If you can kill the DNA and you can touch the protein to DNA like this, and certainly like hydrogen bonding, yeah. But how it will be? You can have the special protein to to kill DNA cancer, because DNA cancer also maybe it's very very specific. Yeah. I think so that's why I like to know whether in the future there will be like that. So
Yeah. I
here,
guess that's very reasonable question though, Bu Jarwani. The apart from that, we probably, since we are from different fields of expertise,
yeah,
probably it is not easy still to us to really be able to follow how actually the simulations can also explain this. But I think it is reasonable to raise question as to whether
yeah,
the study can lead us to understand, let's say, how to prevent SARS-CoV-2 virus, right, from being able to attach to the human ACE2 or to whatever whatever the acceptor of human body, right?
Yes.
To prevent a person to be COVID affected.
but here
So,
this one is also interesting. Yeah, about the DNA with the protein of SARS. Yeah,
yeah.
yeah,
Okay.
yeah.
Okay. Okay, Majidi, may I?
You can
Because
answer that.
I'm really blind, you can explain from the really
From the scratch.
really blind, so that's really really I cannot follow properly really.
Mhm. Okay, what happens when this virus came and binded? From this study, we just understood that this virus SARS-CoV-2 and our receptor binds in 3 different regions.
Mhm.
We identified them, and in the future, what one can do following this work, they propose some ligand which binds with our human S2, our receptor, the same receptor, with higher binding free energy than 1.3 kilocalorie per mole. In that case, what happens when this virus was binding with us, that will be detached because this other ligand will come and that binds with more energy. So we just proposed up to now this much is the binding energy. That's what we could propose. But this work can be taken by pharmaceuticals designing, drug designing people to understand, to design new drug for the purpose.
Mm-hmm. Yeah.
So this is the one of the ways people generally design drug. First, we need to understand this mechanism.
Yeah.
How much binding energy is there? Then you need to find some molecules which has higher binding free energy than this.
Yeah. That's
So this is I mean, somehow a couple of my students are still working on this project actually to complete, to have complete understanding of binding mechanism of all these different variants. You see, there are
that's what I was going to ask also.
15 different variants of this SARS.
Yeah, what's the difference between different variants though?
They just when one of the amino acid is get mutated.
Okay.
Instead of this carbon place, some other things comes and remains there. The structure remains different. So in some cases, for example, I did not present here, but one of my students had carried out some calculations. We compared the SARS-CoV-2 delta, beta, this wild type, mu, kappa, and we found that in delta variants, much more hydrogen bond happens with our body than all these.
I
So
see.
this also explains why this Delta variants was so severe and it
Okay.
killed so many people, especially in India, our region.
Mm.
Oh, yeah.
So it helps us to understand one part, these things. I mean, we are physicists, we just try to understand from physics point of view. I'm sorry that there are some terms of biological physics terms, some from biology also, I could not simplify them. However, what we did, if we see from broad point of view in our presentation today, this is just thermodynamics, free energy calculation, free energy estimation of these protein and DNA protein interactions. So this work could be helpful for drug designing also.
Mm, mm, mm.
So yeah, and that's very nice. So you the first time you do with the SARS, yeah, how to try to find the protein have a binding energy more than that, yeah.
Yes, yes.
Yeah. So maybe afterwards, because in the future,
Yeah.
if there is a formula and there is specific proteins who could kill the DNA cancer, that will be very nice also.
Yes, yes.
That's really, if in the future like that, will be very very you will what do you call it, I mean your innovation will be swing the world, really.
Pardon?
You will swing the world.
Swing the
Yeah,
word.
yeah. Thank you. Thank you so much.
Yeah. Okay, thank you very much.
Thank you. Thank you, Zarwani.
By the way, Narayan, as I don't really understand the difference between vaccine and
Mhm.
medicine.
Mhm.
So, what is more or most relevant from your study towards developing vaccine or medicine to?
No, this helps for developing both actually. Vaccine people also needs to understand such things. Medicine obviously needs, but directly related to medicine.
Medicine. All right. All right.
So
I see.
similar binding free energy and other things we are going to actually testing for this medicine proposed by Pfizer.
Okay. Whoa. So, in some way, so you've also been interacting with Pfizer?
No, not.
Okay.
I am not interacting, but you get molecule. You can just find out how much binding free energy is there with this Pfizer's medicine and our human body,
Okay.
and so that this virus
Okay.
runs out.
Yeah. I thought you've been kind of
No.
initiating some collaboration with Pfizer.
Not yet. Yeah.
Okay. Oh, by the way, well, this is because the other people over here haven't tried to propose questions. Then I'm taking initiative to keep talking and asking questions to you. But really, if there is anybody who would like to ask questions, feel free. I'm seeing Pak Purnomo Suharso interested in asking question.
Yes, but I'm sorry. I didn't follow from the beginning actually, but maybe just a simple question.
Yeah, Pak, simple is even better. It can be understood by other people over here also.
Is it possible for your system to induce, I mean, induce artificial mutation, for instance?
Yeah, artificial mutations also can be modeled and studied like this. I mean, it helps us to understand artificial mutation. Obviously, this methodology, what we use here to understand the binding mechanism of this SARS-CoV and our human body, of course, can be utilized to understand these artificial mutations also. But I have not done yet.
Interesting.
Okay, thanks.
But at least for the mutations that have occurred so far, have you, to some level, probably came up with some understanding of why these viruses tend to mutate, over
Well,
time?
that no. We just wanted to understand why some variants are severe and why some are not, from physics point of view, from just this binding free energy. This is just free energy, U minus TS.
Yeah. Oh, okay. By the way, as you're mentioning about free energy, U minus TS, that's a Helmholtz free energy, right?
Yeah.
As temperature is involved in there, are your calculation really involving temperature explicitly?
A temperature explicitly 310 Kelvin.
Oh, I see. Okay.
Our body temperature, we maintain exactly body temperature.
So this is actually what distinguishes between first principles, quantum first principles calculation, DFT, and this classical one, right?
Yeah.
Because as far as I understand, DFT
is just for
the theory for ground state only. Right. Okay. And one more probably naive question from a person who is outsider of this field. If I look at the pictures you show about the objects being involved in the simulations, so you are not just dealing with atoms or objects that may be considered having spherical shapes, but you really you visualize your objects being some things like helical things, like helical ribbons. Okay. So in your simulation, how do you really actualize that in the
we can visualize all those things. There are
and not just visualize, I mean to include it in your calculations.
I mean, to include means what to include, sorry?
Yeah, I mean, how do you make the shape? How do you say, how does this shape, how does this shape enter into your calculation?
Okay, what happens, we take initial structure from crystal structure, from X-ray diffraction, from some experimental people at the beginning. And then there will be this force field designing. And then once you start your simulation, all the structure and other things, it takes itself.
Okay.
So our input is only the X-ray crystal structure we obtained in literature.
I see. I would imagine that if we can say in terms of number of particles, number of entities involved in your simulation,
huge number.
Huge number.
It's 220,000. I did not show water molecules because this DNA protein in our body, there are a lot of water molecules involved. Okay.
Okay.
So to understand that there are all the water molecules also, I did not show all the complete picture because that is generally understood matter. Because and protein interactions, that's also contains water around them. So these hydrogen bonds and other things form by the help of water also. So in total, our this protein system contains 222,000 atoms.
Okay.
It's really huge system.
Okay, as far as the implementation of classical versus quantum principles implemented in your simulation.
Mhm.
As far as I understand, molecular dynamics is mostly classical, right?
There
it is
is
based
quantum
on.
molecular dynamics also, but I have not done that because it's
Okay.
really time consuming.
All right,
In
all right.
quantum molecular
The,
dynamics,
the one
initial
that you.
molecular dynamics, what you do, you don't need to take force field from somebody else.
Mhm,
You have all these systems, keep all these atoms with electrons, clouds, and so on,
mhm,
and solve the Schrodinger equation and find the force
mhm.
from that energy. And on the fly, when you move it, again solve Schrodinger equation like this. I mean, there are methods like this. That is actually developed by Carr and Parinello from CISA, ICTP.
Oh, I see. Does the package you usually use also provide both classical and quantum?
There is package, but I don't use that because you see, to carry on this computer, this ab initio quantum simulation,
Mhm,
not like DFT molecular dynamics,
mhm.
quantum molecular dynamics, it really needs huge amount of
Okay.
this computing facilities and
Okay.
storing also.
All right. Right.
So that's why I did not pursue it actually.
Okay. So then I'm concluding that so what you do is the classical version of molecular dynamics, right? But then that makes me have a further question about then how do you identify hydrogen bonds or other chemical bonds if you only rely on Newtonian physics in this case?
No, by distance
Mhm,
between two atoms.
mhm,
I mean, we check the distance between two atoms for long times, say
mhm,
100 nanoseconds, 1 microseconds like this.
mhm.
How does this changes? We analyze the trajectory. From that, we can find out
Okay. So it is not that you
other type of
need
force like
to
van der Waals like this.
look at the wave functions
No,
stuff like
we
that. No.
don't look at the wave function.
All right.
Yeah.
Okay. Well, it is very interesting. I'm curious about how big the computing facility that is required, for doing such a simulation.
As I already mentioned, there are 5 servers
5 servers, not
and
that
100 core
many
machine.
though.
200 core machine we have total.
200 cores. Huh?
Yeah.
Oh, okay. Yeah. I think that's about similar
And one
power.
Majidi, one more thing is that what you need, GPU is really fast for molecular dynamics,
Okay, you're using GPU.
not CPU.
Oh, I see.
And some GPUs are good for phonon calculation also in quantum. So it depends what type of, I mean, computer architects is also important for type of problems you try to solve.
I see. Interesting. So, as you said, you also have other area you usually do that is separate from this one, right? Which is the ab initio DFT, right?
Yeah.
Okay. In any level, do you have any? I mean, are you seeing any need of extending this this study? I mean, by extending, I mean to involve more people. I mean, to extend your collaboration.
Yes, of course.
Along
That's
this
what we
direction.
always need and want.
Yeah. Are you considering to have collaborations with completely, with people who are completely new, or even at the moment being still outsider of the field.
Yeah, that's also possible. That is also possible. As long as he or she is student postdoc to learn, that is possible.
Yeah. Well,
And
I would consider
recently,
it. Yeah, if I could find.
Recently, our department has become this affiliated center of ICTP.
Oh,
So
great.
sometimes
Great,
they
great.
support students also.
Oh, by the way, I also wonder about the number of master's degree students you showed in your presentation. Are you saying that is one batch?
Yeah, one batch,
One batch is 100 something?
120.
Only for physics?
Yeah, only for physics. No, the number reached up to 720 also in different campuses of our university.
For total master's degree students for all fields?
Yeah.
Okay.
No.
Hmm?
Physics.
Physics only?
Yeah.
700?
No, Nepal is a country where students were showing placards to government that, okay, please allow us to study physics. And there was protest.
It's amazing. It is only in your university, right?
Yeah.
How many universities in Nepal do you have?
No, there are many others, but physics.
This is
physics is
the
only
topmost
this
university.
They are
in
going to
Nepal, right?
open in other universities also.
Right. But 700 is a very amazing number,
But now the number decreased to 200,
Okay.
260 students.
Still, if 200 is only people, doing one field, of research or study, I think that is something rare to happen in.
Yeah, and I have to
in many countries,
yeah,
in the
I
world.
have to supervise large number of students. If you see the statistics.
Yeah, that's also what I want to know. How your faculty
I
staff can
showed
handle this many.
for the United States of America, our country is third country to export. I mean, to make US non-US students graduated from US universities. I mean, about 2,000 students get graduated for year in US. 1,800 to 2,000. Out of them, about 50% are non-US students. From them, about 300 are Chinese. 150 like Indians, and more than 75, 80 are Nepalese.
I see. That's amazing. That's amazing.
So this means this number is huge. So at least about 100 students from our university, our department, the building, what I showed, every year they go to US, more than 100 students.
What is your population, country population?
30 million.
30 million. So compared to us, we are like 2,050 millions. But the number of students going for postgraduate study in the US is much less compared to
yes,
yours.
yes. We are third in whole world. Going to, I mean, if you just compare number of students going to US to pursue PhD in physics. Okay, I'm talking about physics only.
Just physics. What about the other fields? Is the tendency the same or not?
Other fields also go. If you see recent years numbers, highest numbers of students come to US from China, then India, and then Nepal. In undergraduate also.
For India, China, no wonder, because I mean the population is big. Okay, they have even a bigger number of population compared to us. But Nepal is more. Okay.
And
well,
Majidi, I wanted to inform you that this number was not like this before I came. When I joined, suddenly this number increased. Not suddenly, gradually this number increased and reached this one.
What's the
So
factor?
this is what is impact of us also. That's also I was saying.
Okay. That's because of you, partly. Right?
Partly, yeah, of course. Of course. Partly, yeah.
Great. Great. Well, Narayan, I would consider if I have, if I have more students to come to me requesting to be supervised for their bachelor's thesis project, then I may probably try to take them, for our probably starting initial collaboration on some kind of joint supervision.
Yes, yes,
If possible. So what I mean by this is, if we want to start doing research in the field that is more from your expertise rather than mine, then obviously I would let you lead, the project. But of course, since the students is ours, I mean, belong to our institution, then officially they may be under me officially, but I mean, more technically, I would be really happy if you would be.
Sure. I will be pleased to do so, actually.
Yeah. And also not just this molecular dynamic simulation, but also the other one.
DFT is
and I guess
another area.
The other one is
really
probably not more related. We probably can start thinking about something feasible. Which is probably closer compared to this molecular dynamic one.
Yes.
Since I have also been using DFT approach as part of my overall research work. So okay, well, since we formally we still have some time, I would offer other people, if there are still maybe students, if any students may like to
probably
ask
this became too far from the area what's going on in your university. Time when there will be few students we supervise jointly, then they may ask question in such.
Sure. Okay. Bagaimana nih mahasiswa medis Irna Jelita? Saya lihat ada nama nih Irna. We also have faculty members, not quite many, but a few joining us. But they are all, of course, as I said, we don't have faculty members focusing on this field. So if we have faculty members attending our seminar today, they are also outsider. So, but I would like to invite Pak Terry or Pak Adam if you have questions on anything.
No, Pak Aziz, I don't have question because this is
all right. You are here
beyond my subject. But anyway, I saw a very intense discussion, so I can feel that the topic is very hot, and I think Pak Aziz understand this topic also.
A little bit. Okay, Pak Adam, ada nggak pertanyaan mahasiswa nih, MJ? I guess if there is no more question, so we have the custom that to end formally the seminar on behalf of our physics department, our professor who is with us here now, Professor Dr. Terimat, will symbolically give you a certificate of appreciation as the speaker of our seminar today. Mbak Fitri, apakah sudah siap? Tolong diperbesar ya.
Sudah maksimum kayaknya.
Wah, ya nggak apa-apa deh. Silakan Pak Terry.
Okay, Professor Adhikari, I would call you. I should call you Narayan or Adhikari.
As you like.
Okay.
Officially Professor Adhikari, but as a
Okay.
friend, I usually call him Narayan.
Yeah.
Okay. So I would like to become also a friend of you. So I would call you
Thank you.
Narayan.
Sure,
So
sure.
Narayan, we are very happy to have you here as a speaker in the physics seminars. We have the so-called Rebo, and I cannot translate it to English. Rebo is Wednesday, but maybe
Yeah.
Aziz will will translate it to
Yeah.
English. So every Wednesday we have this seminar.
Yeah.
So today we have you in this seminar. We thank you very much. And I think this is what the department could give to you as a souvenir. This is a certificate. But anyway, we thank you very much. Department of Physics very happy to have you here. And I think in the future, maybe you would also possible to
Yeah.
give another talk. We are very
Yeah,
happy today.
yeah,
Thank
yeah.
you. Thank
On
you very
another
much.
topic.
Thank you.
Yeah.
It is my great pleasure to be here. And I always appreciate your recognition and kind invitation.
Okay, thank you. Please
Thank
pass
you.
this.
Thank you.
Thank you very much, Professor Terry Mart, for your time to give this certificate of appreciation to our speaker today, Professor Narayan Adhikari. And so Narayan, with this, I'm going to close this seminar officially.
Thank you.
So on behalf of the Physics Department of the University of Indonesia, we thank you very much for your willingness to share your knowledge and experience and everything, and information about your country, which is kind of inspiring to us and makes us ashamed actually as the country that has a lot more number of people, right? More populous country. But you know, we are seeing the fact that Nepal has been a country that has sent their people to study abroad, especially in the United States, for postgraduate studies with a large number, which is kind of make us feeling underrepresented compared to our number of population. But hopefully this kind of information can stimulate us, you know, to be in a better position, to be improving anyway in whatever aspects related to improving our country from the education and research sides. Okay, thank you very much.
Okay,
and,
thank you so much.
See you
pleasure to
again
be
in
here.
any occasion,
Yeah.
either virtually or in person if possible. Actually, I've been dreaming of going to Kathmandu though.
Yeah, please visit us. Now it became informal, okay?
Oh, yeah. So how far is it from Mount Everest? From the
About 100 kilometers, 150 kilometers like this. But you can see Mount Everest when you come here.
Okay.
That's not bad. I watched the movies 7 years in Tibet. Yes, so I think it's also included Kathmandu. Yeah, 7 years in Tibet.
Yeah.
Okay.
Okay. Yeah,
Okay.
thank you very much. Thank you very much, Professor
Bye-bye.
Adhikari. Thank you
Bye-bye.
very much, all the participants, you know, who've been patient enough, you know, to listen to our discussion. until we finally close this seminar. Thank you very much and good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikum salam.